Refraction and Snell's Law. Here are your priming questions. Refraction. We've talked about this before as a wave as it hits a boundary, and we said that part of the energy of the wave is reflected back and part of it moves forward into the other material. And so when it moves into the other material, it is a refraction. And when we specifically talk about light, we are going to be talking about the bending of light that results from this changing speed. And so when we say bend, it's not a curve, it's more of an angle. It changes the direction that the light is going. And the way we quantify this is through the use of the index of refraction, which we have as a ratio between the speed of light, the c, that's our speed of light, that's 3 times 10 to the 8th, and the speed of light in the medium, so that'll be the v, whatever the speed of light in that particular medium is. And so what you should notice here is we should always have the greatest value on top, our c, so that means that our v should always be less than the speed of light in a vacuum, because that's going to be the fastest that light can go, which means that all of our values for n should be positive, first of all, and should be greater than 1. So 1 plus. 1 or greater is for their values. Now there are going to be some special materials that you might learn about in the distant future that have some pretty interesting properties, but for the scope of our class, we are going to be limiting our indices of refraction to greater than 1. Now, here are some common indices of refraction. What I want you to pay attention to is in a vacuum, so that's going to be C over C, so that's going to be a value of 1. Air at STP, that's standard temperature and pressure, it's 1.00029. But if you think of the practice problems and the problems that we do typically in class, we don't have this many significant digits, so typically for air, we just use a value of 1. So we don't worry about the 0.00029 part of it, because for our calculations, it actually won't make a difference when we take our significant digits into account. The other one that I want you to memorize is typical crown glass at 1.52. This is a very common one that we're going to be using. And what I want to show you is one of the highest values for a naturally occurring mineral is diamond at 2.417. And I recently read an article that some scientists created a metamaterial polymer with gold or aluminum lattice structures that had an index of refraction of 38.6, which is an incredible value for the index of refraction. But the ones that you'll want to memorize are for air, it's going to be 1, crown glass at 1.52, and diamond at 2.417. So this brings us to Snell's Law. And this is a way to quantify how much that light bends in the different materials. And again, when we say bend, we're talking about the angle that it changes. So the angle of refraction depends on the angle of incidence and on the indices of refraction of both media. So we have N1, N2 are two different mediums, the index of refraction of both, and theta 1, theta 2, the angle inside that medium of the light. So we have N1 sine theta 1 is equal to N2 sine theta 2. It's a very simple equation. What you do need to pay attention to, though, is our thetas, our angles, are going to be measured in degrees. So you need to make sure you have your calculator set to degrees and not radians. And you need to make sure that your n values are greater than 1. An acronym that I like to use to check my work is FST SFA. So fast to slow is towards, and slow to fast is away. And what this means is if you go from a low to a high index medium, remember a high index is going to mean a slower speed of light, then the way this will bend is towards the normal. This is, remember, all of these angles are measured in relation to the normal, okay, for our thetas. And then slow to fast, so a high index to a low index will bend away from the normal. And I'll show you what that means in just a little bit. A conceptual item here is for mirages. So the reason why you see a mirage is because of the hot air above the ground causes the light to refract. I've shown a diagram here. So you have the light coming in from the sky, and as you have these heat waves, it actually changes the medium of the air, and it refracts the light to your eyes. So it actually will bend the light to your eyes due to that change in temperature above the ground. This is also the reason why and how a prism is able to separate the white light coming in to the rainbow, the Roy G. Biv, going out. For a particular medium, the index of refraction is actually dependent on the frequency of light. For that metamaterial that I was talking about before with the 38.6 index of refraction, that only works at 0.35 terahertz. So it's not even in our visible range, but it works with a different region of the electromagnetic spectrum. And so because different frequencies of light travel at different speeds, they will bend differently, more or less, allowing the prism to break up the light into its separate colors. This is also how spectroscopes are designed. Now, going back to FST and SFA, what I've first shown you here is if N1 and N2 are the same medium, and if they are the same medium, so if it's air to air or glass to glass or water to water, something like that, the beam of light will go straight through. I've done my best to show it as a straight line. Now, if the medium begins to change, what will happen is if the light is incident from the top and refracting through the bottom, this ray will either bend towards the normal or away from the normal, depending on whether your second medium is a slower medium or a higher index, another way of saying it, or whether it is a faster medium or a lower index compared to your N1. So, for example, if we do FST, if it's fast to slow, which means it's a low to a high index medium, this will bend towards the normal. It'll look something like this, and I've exaggerated it a little bit here. And so if you see light coming in like this and then bending towards the normal, we know that we are going from a fast to a slow medium, and it's going to be a low to a high index of refraction. On the other hand, if we see that it bends away from the medium, bends away from the normal like this, we know that we have a slow to fast, so slow to fast, so a high index to a low index medium will bend away from the normal. And again, this is the surface, and this will be our normal line. And so, we'll do a quick practice with Snell's Law. Light in air is incident on the surface of a glass slab. In the air, the beam makes an angle of 40.0 degrees with the normal to the surface, while in the glass, it makes an angle of 28.0 degrees with the normal. What is the index of refraction of the glass? And so we can just use Snell's Law here, and we can start listing things out, N1, N2, and then theta 1 and theta 2. And we'll go ahead and say air is our N1. That is where the light is incident, so it's easiest to say that that's going to be our N1. And we know that the index of refraction for air is 1. We are looking for our N2. Our theta 1 is 40 degrees, 40.0, and our theta 2 is 28.0 degrees. And so all we have to do is think of our equation. N1 sine theta 1 is equal to N2 sine theta 2. When we start plugging our values in, so 1 times the sine of 40.0 is equal to N2, what we're looking for, times the sine of 28.0. And that should be in degrees. And when you work this out, and you want to check my work just to make sure you're getting the same answer, you should get N2 is equal to 1.37. Now, I want you to do this practice problem, parts A and B, for practice and for homework. We're going to check these in class. You need to at least attempt these and show your work for Snell's Law, a ray of sunlight, and go through that problem. And here are your primary questions again. And we'll check these in class.